Well, it seems that IP is at it again with his nonsense about quantum mechanics proving the existence of his God, so let's see if he's still parroting this same bullshit.
One of the biggest objections to the view that a conscious observer is necessary to collapse the wave function is that collapse is really only caused because of interaction with a measuring device. In other words, it is not the act of an observer measuring that causes collapse. What really happens is the measuring device interacts with the particle and causes it to collapse.
That's correct. Collapse is caused by a measuring device. However, collapse is not something that happens to a particle. Collapse is something that happens to the wave function. Here, look at this plot. It's supposed to be a rough plot of the wave function or probability distribution of a fair six-sided die. Each side has a probability of 1/6. Now, this is what happens to the die when the wave function collapses and I roll a 3. Collapse is something that happens to a mathematical probability distribution. It's an abstract phenomenon. The conscious observer causes collapse in the sense that the observer gains knowledge of the upside value of the die when it's rolled.
The conscious observer has nothing to do with this. We've already dealt with this objection thoroughly in our video, The Measurement Problem, in our video which explains the delayed choice quantum eraser experiment. But what if there was an interaction-free experiment? An experiment where particles have no interaction with the measuring device and collapse is still caused. Well, in fact, there was just such an experiment performed in 1994 by Anton Zellinger and his team. The paper on the experiment was called Experimental Realization of Interaction-Free Measurements, and they directly demonstrated what we have shown to be the case in other videos.
Wrong.
That interaction is not the cause of ultimate collapse, but it is the knowledge of which path information that actually causes collapse.
That's correct, in the same way that knowledge of the die's upside value causes the wave function of the die to go from this to this. It's not that the particles have different properties, it's that the values of certain observables like speed or momentum or spin have been returned. You have to understand that at the quantum mechanical level, a variable like speed is not a property that is necessarily intrinsic to a system or a particle like we would like to assume at the classical level.
Here is a simplified explanation of how the experiment demonstrated collapse without interaction. Take the double slit experiment. Firing particles at a double slit will cause them to act like waves and interfere with each other, causing an interference pattern on the other side to appear. This is because we don't know the exact location of each particle, so the probability distribution for each particle acts like a wave and spreads out. However, if we attempt to find the exact location of the particle, we can place a measuring device over slit A, and now, because we know every time a particle travels through slit A, we'll know the exact time it goes through slit A, thereby giving us its location. Astonishingly, the fact that we know the location of all the particles that go through slit A changes how the particles are. Now, they no longer act like waves, but like particles, or little bits of matter, and therefore no longer create an interference pattern, but a clump pattern, meaning little bits of matter went through the slit, not spread out waves. The result changes, and therefore the particles have different properties just because we decided to measure their position. So basically, if we don't know the exact path, or which slit the particle goes through, it spreads out and acts like a wave. But if we place a measuring device at one slit and find out which slit it goes through, then since we know the exact path it took, it acts like a particle instead of the spread out wave. Now some say the measuring device is just interacting and causing the particle to collapse from a wave into a particle, and thus collapse is just caused by interaction. Interfering with the wave causes it to collapse to one definite position. But there is an important key element missing here, and that is, if we place a measuring device at A and shoot particles at the double slit, we have not placed a second measuring device over slit B. However, when particles go through that slit as well, they also collapse to one definite position.
That's because you have added a detector to the system. The fact that you have done that is what causes collapse. That's because not going through A necessarily entails going through B. For example, In the old Stern-Gerlach experiment, the experiments that were used to demonstrate that particles had a property called spin, particles were shot through a magnetic field in order to measure their spin. If they went upward, they were spin up, and if they went downward, they were spin down. The magnetic field functioned as the detector because it was used to register the value of a certain observable, in this case, spin. In the experiment that IP is citing, the detector is added to the system. You could add the detector to port B and not A, and you would see the same thing. The diagram you see here shows the setup of the experiment. The purpose of the experiment that IP is citing in the paper is to solve a problem regarding the detection of a hypothetical bomb. In the Stern-Gerlach experiments, shooting a stream of electrons randomly would have them go all up and down the wall on the opposite side. However, in the presence of a magnetic field, which detect the spin, the electrons would either go up or down, but none of them would hit the middle,
even though there was no measuring device there to interact with. But how could this be? If interaction is causing collapse, then they could only collapse when they go through A, not through B.
We know that if the electrons didn't go up, it must have went down and therefore must be spin down.
But what is causing collapse in slit B? The only logical conclusion is what we've been arguing for in previous videos. The only difference that happens when there is no measuring device and when there is one placed is our knowledge of the system. When there is no measuring device and the particles are randomly shot at the double slit, we have no clue which path they take.
That's correct. The only difference is the value of a particular observable, in this case, position, is returned. In the same way, the only difference in respect to a particle's being spun down is the path it took through the magnetic field.
So the probability distribution of where the particle could be spreads out. However, if we measure at one slit, we know the path information, and we know when a particle goes through slit A. And we'll also know if a particle doesn't go through slit A, but makes it to the other side, it could only have gone through slit B. Therefore, the only difference in regards to slit B is the path information the observer, we, know about the system.
I see. So what IP is doing is equivocating on the definition of collapse. There is collapse as an abstract notion in the case of a dye's wave function that I showed earlier, and there is how that collapse is physically manifested. The two are not the same, although it is tempting to claim them as such. We can run the Stern-Gerlach experiments and choose not to look. However, the particle will either go up or down whether or not we look, but it will not go in the middle. The mind enters in because the probability distribution that we created goes from this to this once we have ascertained that the upside value of the dye is 3, or, in the case of the Stern-Gerlach experiments, that the particle is spin up.
And collapse is about what the observer knows, not about interaction. The experiment coheres with the other data we have gone over. Quantum mechanics provides us with a picture of reality that our knowledge or choices affect the experimental outcome.
No, our knowledge affects the probability distribution that we created to model the values that a particular quantum mechanical observable can take.
Dumbass!